Okay, welcome back. What I want to do today is to look at DC machines, okay? And basically, we're going to look at the magnetic field that is set up around a current carrying conductor. So when we pass a current through a conductor, there is an electromagnetic field set up around that conductor at all stages. It doesn't matter the voltage size or the amount of current flowing, you will still have an electromagnetic field around that conductor. Okay. Now here we have, make sure I can get it in frame. Okay, 1 second. Okay, good. Yep, we have it in frame. Here we have principle of operation of a DC machine. All motors and generators make use of two basic principles. When two poles of a magnet are brought close together, then there will be either a repulsion force or an attraction force. Okay, and you know that from school. Okay, when current flows in a conductor, a magnetic field is created around that conductor. Okay, and here we have our magnetic field. Now remember, the magnetic field flows from north to south, always from north to south. It does not deviate from that, okay, north to south, and you can see that there flying. So if you imagine this to be a bar of magnet, and you have like a toilet roll, for instance, imagine that, and you pass this through the toilet roll backward and forwards, you would induce a small electromagnetic field within that toilet roll, providing you have a coil around it. The coil only needs to be 1 or 2 turns, and the end comes out somewhere. You'll find that you'll create a simple magnetic field. Okay. Okay, I'll leave it there because I think it's relevant that you understand this concept. Okay, right. We're still looking at magnetic fields, okay? And here we have current flowing in the conductor. Now, here we have the current flowing towards you. Imagine this to be a tip of an arrow, and the current is flowing towards you. So you can see that when current is flowing towards you, it flows in an anti-clockwise direction. And that is important to understand, that it flows anti-clockwise when it's flowing towards you. Now, when it's flowing away from you, you can see that it will flow in a clockwise direction. And here we have our arrows telling us what direction it is. That cross means that it is flowing away from you. Imagine that you're looking at the end of the flight of an arrow. Okay, that's flowing away from you, and you can see that when it's moving away from you, it's actually the magnetic field is going clockwise. Okay, and that is important to be able to recognize that. Okay, now, magnetic field in a coil. When a current is passed through a coil, a magnetic field is generated. Okay? Excuse me. The armature windings start and finish at a point on the armature called the commutator. And let me just bring this up for you so you can see that in full. Okay. I'll read the text on it as well. Okay. Okay. Good. Now this brushes. Now the final part of the machine is the brushes. The brushes on a DC machine are made up of carbon. Carbon has a number of qualities that make it ideal for this purpose. It is very soft. It is a conductor. It self-lubricates. The rotation of the machine causes the carbon to weigh down and acts as a lubrication, thus reducing friction on the carbon brush itself. Okay. And here we are. Let's see if we can get this into play fully for you. Okay. Okay. Bring the other one into play as well. Okay. Okay. All right. Good. Good. Okay. So let me just bring it back into focus while I bear with me for a second. Okay. Thank you. Now you can now see that here we have, for a DC generator, the brushes act to tap the supply of the armature. The brushes act as conductors and lubricators. For a DC motor, the brushes act to deliver current to the armature, where again the brushes act as a conductor and lubricator. Okay. Now, commutation. A commutator is made up of a series of segments which are conductors separated by thin pieces of an insulator such as mica. Now, mica is a insulating board. It's basically made up of what we used to call compressed paper, okay, with a varnish coating on it, and it is quite an efficient insulator indeed. Okay, let me just make sure that we got this in full view. Okay. And let's go down a little bit, make sure we get this into play. Okay. Okay. Now pan back a bit. Okay. Okay, thank you. Good. Okay. That's the main thing. Alright, we have it all in frame now, so it should be okay. Right, that's fine. Okay, good. Okay, so that's what your commutation looks like, and that's the effect of whether it's a generator or whether it's a motor. Okay. And here we have a DC generator. Now here we have a single coil of cable going right round. Okay, so it's one end is connected to one half of the commutator, and the other end is connected to the other half of your commutator. Okay. Let me see if this will run as I click it. Okay, sorry, no, it doesn't. Okay. Okay, sorry about that. My apologies. Okay. Undo. Okay, sorry. Right, we have to go back a little bit. Give me for a second. Okay. You've seen that already. Bear with me for a moment. It's okay. Sometimes these, if I press the wrong button, it sends me back to the beginning. Okay. Right. Thank you. Now I just want to show you how this works. Okay. Now this is a piece of imagine this to be a piece of wire. Okay. And it's fixed on to either half of a commutator. These are our brushes. Okay. And we're taking the supply off. That's going to be our waveform here. Okay. So, and this is what happens when we begin to rotate the conductor in the magnetic field. Now again, you remember we said north and south, so you can see here it is rotating clockwise. Okay. And here you can see that it's actually producing a waveform. So every time it cuts through these magnetic force, that is the waveform it will produce, because it is a DC generator. Okay. Okay. And that'll be it for now. Thank you. Okay. I hope you would have found this useful, and have a good day. Bye bye.